Hey viewers, so welcome to another edition of NAMSSN tutorial. So this is differential equation. So I want to talk about method of solving second order differential equation. So this is a method of reduction of order. So in the previous mathematical method, we learned how to solve differential equation by using we have first order and second order. So for first order, we have several methods of solving it: linear equation, homogeneous, exact, and inexact. For second order, we learned how to use undetermined coefficients. So here now, this is reduction of order. So if I'm having something like dy dx equals to, let's say, x squared. So that means the rate of change of y with respect to x is x squared. So here now, this y is the dependent variable. Y is the dependent variable and this x is the independent. That is, so y depend on x. So for this reduction of order, we have about 5 cases, but then we are going to limit it to just 2 cases. So case 1 is when the dependent variable variable y is absent. That is, there are some differential equation that y will not be there. So for example, let's try to solve 1 plus x squared d square y dx squared plus x dy dx plus ax equals to 0. So where a is greater than 0. So look at this differential equation now. You observe that we are only having x, x, x. So this is just dy dx. So this one fall on case 1. The dependent variable y is absent. So look at another example. Suppose I'm having e raised power x squared over 2 open bracket x d square y dx squared minus dy dx. Everything is equal to s cube. Look at this kind of differential equation too. You observe that there is no y. So there is no y. So I'm going to solve these 2 examples based on this case 1. So let's say this is 1, this is 2. Solution to first one. So we are solving 1 plus x squared d square y divided by x squared plus x dy dx plus ax equals to 0. So the transformation we are going to make is that we are reducing the order. So initially, the differential equation is in second order. The highest derivative is 2. So we are going to reduce it to first order. Then we use our knowledge of first order approach. So now we are going to say let dy dx, we can assume that dy dx equals to anything, it equals to any letter. So let's say dy dx equals to t. So if I take the derivative of both sides, so that means d square y dx squared, it will be dt dx, right? If I differentiate this, I'll have dt dx. So just substitute for these 2 guys into this differential equation. If I substitute for dy dx and d square y dx squared back into my differential equation, so what I'm going to have is 1 plus x squared dt dx, because the square y dx squared is now dt dx, plus x and dy dx is t, so x and dy dx will be tx or xt, then plus ax equals to 0. So what do you observe? From second order, we have reduced it to first order. So what I'm going to do now is that this 1 plus x squared is carried, so I have to divide through by 1 plus x squared. So if I divide through by 1 plus x squared, I'm going to have dt dx plus x over 1 plus x squared with t, right? Then plus a over 1 plus x squared equals to 0. That is when I divide all through by 1 plus x squared. Now, the next thing is that this first order differential equation now, which one does it look like? So dt dx plus something t and ax over 1 plus x squared equals to 0. So if you remember from our linear differential equation, recall that anytime we are having a linear differential equation is in form of dy dx plus a function of x with y equals to a function of x. Just like equation of straight line, y equals to mx plus c. So what we're having here now is a linear differential equation in terms of t and x. So what I'm going to do is that I will bring this to the other side. So this one will change to dt dx plus x over 1 plus x squared t equals to minus ax over 1 plus x squared. And how do we solve linear differential equation? We use the method of integrating factor. So dt dx plus this x over 1 plus x squared. Now look at this one, dy dx plus p of x times y. Now dt dx plus everything there is a function of x times t equals to a function of s. This is a function of s. So we are going to use integrating factor. So what is integrating factor of this differential equation? Integrating factor is a exponential integral of what is here? Exponential integral of x over 1 plus x squared dx. And what is the integral of x over 1 plus x squared? Using your u substitution, let u equals to 1 plus x squared, du will cancel this. So this will be exponential half ln 1 plus x squared. So because of ln and properties of logarithm, you know, if I'm having log m raised to power n, it will turn to n log m, right? So we are having half log 1 plus x squared. So we can say that our integrating factor is exponential ln 1 plus x squared all raised to power half. We can change the coefficient to the power. And don't forget that e is the anti-logarithm, ln is natural logarithm. Two of them will cancel out. So our integrating factor will be 1 plus x squared all raised to power half. So if that is our integrating factor, so what will now be the solution of this differential equation? So the solution will be t, or the solution will be t multiplied by integrating factor, this side multiplied by the integrating factor equals to integral of the other side here, integral of minus ax over 1 plus x squared. That one to multiply by integrating factor, we integrate with respect to s. With respect to s. So we are going to have t, this is our integrating factor, 1 plus x squared all raised to power half equals to integral of minus ax over 1 plus x squared times 1 plus x squared all raised to power half with respect to x. So how will I integrate ax over 1 plus x squared and another 1 plus x squared? So this is like 1 plus x squared raised to power 1. This is 1 plus x squared raised to power half. Half minus 1 indices. So this will be minus ax over 1 plus x squared raised to power half. This is what we are going to have, right? Because half minus 1 is minus half. So equals to t into 1 plus x squared all raised to power half. So from here now, what are we going to use? How will I integrate? Don't forget, a is just a constant, so it doesn't give us any problem. U substitution. You say let u equals to 1 plus x squared. If u equals to 1 plus x squared, du dx is equals to 2x. So this side we are going to have integral of minus ax divided by u raised to power half, right? And from here, if du dx is 2x, so dx will be du over 2x. So x cancel x. A over 2 is a constant. So we are going to have minus a over 2 integral of 1 over u raised to power half du. So how do I integrate u raised to power minus half? Standard integral. You add 1 and then you divide by whatever you are having as numerator. So don't forget, this left hand side we are having t into 1 plus x squared all raised to power half equals to minus a over 2. If I integrate u raised to power minus half, you know, you add 1 to this one. So this will be u raised to power half. Then over half. Over half again will give us times 2 over 1, right? Then we add plus c, where c is the arbitrary constant of the integration. So 2 cancel 2. Recall that u equals to 1 plus x squared. So our differential equation is t into 1 plus x squared all raised to power half equals to minus a 1 plus x squared raised to power half plus c. So don't forget, we were doing what? Reduction of order. We reduce the differential equation from second order back to first order. Then we need to make this t to stand alone. If I want to make this t the solution of the formula, I will divide through by this. So if I divide all through by 1 plus x squared raised to power half, we are going to have t equals to minus a, because if I divide this one by 1 plus x squared raised to power half, it will definitely cancel out. Then I also divide this one by 1 plus x squared raised to power half. It will be c into 1 plus x squared raised to power minus half, because if I divide. And again, where are we coming from? What is t? T. Yes, we said that dy dx equals to t. So recall that dy dx equals to t. So change dy dx to t. So this will be dy over dx equals to minus a plus c into 1 plus x squared all raised to power minus half. And if dy dx is that, this is another differential equation. Because from second order, we break it down to first order. Then we have to return it back to where it's coming from. Our answer must be in terms of x and a. So this is dy dx. This is another differential equation. How do you solve this? Variable separable. So cross multiply and integrate. So y equals to integral of minus a plus c into 1 plus x squared raised to power minus half. We are integrating all this with respect to x. So okay. So from here now, y equals to integral of minus a plus c into 1 plus x squared raised to power minus half. So we want to integrate all this with respect to s. A is a constant. Don't forget, a is greater than 0. So if I integrate minus a with respect to s, so y equals to minus ax. A is just a constant. And then what we are having here, 1 plus x squared raised to power minus half. So we can say this is a c integral of 1 over 1 plus x squared. That raised to power half, we can change it to square root like this. Right? And what is the integral of 1 over 1 plus x squared? That's sine hyperbolic of sine. All those standard integral. So y equals to minus ax plus c sine hyperbolic inverse of x. So that is the integral of this. Then we had another constant. Let's say this is c1, then plus another constant c2. Yeah, let's say c1, 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 c1. Yes. So this is the solution of this. You know, if we are solving normal second order differential equation, we have two constants, a and b. So these are the constants, c1 and c2. So that is how we solve this first one. Now the second one, we are solving e raised to power x squared over 2 into bracket x d square y dx squared minus dy dx all equals to x raised to power 3. You observe that y is absent. So variable y is absent. So how do we solve? The same approach. We reduce it by saying let dy dx, suppose we call it t or something, let dy dx equals to t. Then if I differentiate it further, so that means d square y over the x squared, it will give us the t dx. Then we substitute for the square y dx squared and dy dx into our differential equation. So this one will now be e raised to power x squared over 2 into x d square y dx squared is the t dx. So this will be x dt dx minus dy dx is equals to t minus t equals to x cubed. Right? So you observe that from second order, we break it down to first order. So how do I move? How do I move? Because of this e raised to power x squared over 2, let's divide both sides by e raised to power x squared over 2, or we should open the brackets, anyone. So if I divide both sides by e raised to power x squared over 2, we are going to have x dt dx minus t. If I divide x cubed by e raised to power x squared over 2, it will be x cubed e raised to power minus x squared over 2. So the next thing I'm going to do is that I will also divide by x. I will divide all through by x. No, 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 no. So if I divide through by e raised power s square over 2, so this side will be e raised power minus s square over 2. So the next thing, let's divide through by x so that the s dx will stand alone. Divide through by x, we will have dt dx minus 1 over xt. If I divide this side by x, it will be x squared e raised power minus x squared over 2. So this is also a linear differential equation. So not every time the differential equation will turn to linear, not all time, but then the one we are solving here, so they are just turning to linear differential equation. So this is our p of x. From here now, we find this is a linear. This is a linear first order. Linear first order. And then we find the integrating factor. Integrating factor is e raised power integral of what is here? Minus 1 over x. And what is integral of minus 1 over x? That is minus ln x. Because of this minus, this will be e raised power ln 1 over x. And if I turn this minus to this side, right? So e and ln will cancel out. So our integrating factor is 1 over x. So if our integrating factor is 1 over x, what is the solution of this one? So the solution will be t multiplied by integrating factor equals to integral of x squared e minus x squared over 2 multiplied by integrating factor. So integrating factor is 1 over x. This is t multiplied by 1 over x equals to integral of x squared e minus x squared over 2 multiplied by 1 over x. We integrate with respect to x. So how will I integrate? Well, from here x will cancelled, it will remain 1. So we are going to have t over x equals to integral of x exponential minus x squared over 2 dx. So we don't need to use integration by parts, because if I differentiate what is here, if I differentiate x squared over 2, it will definitely cancel out this x. So we say let u, if I say let u equals to minus x squared over 2, and you know that du dx, if I differentiate this, that was minus x, right? 2 will cancel out. So t over x equals to integral of x e raised power u, dx is du over minus x. So x cancelled, we are going to have minus integral of e raised power u. So integral of e is te, so this will be minus eu plus c. And recall that what is our u? Our u equals to where? U equals to minus x squared over 2. So finally, we are going to have t over x equals to minus e raised power minus x squared over 2 plus c. Where let's say plus c1, because we still need another constant here. We need to make this t to stand alone before we can return it back to where it's coming from here. So how will I make this t to stand alone now? This is t over x. So if I multiply through by x, so t equals to minus x e raised power minus x squared over 2 plus c1x. Yes, plus c1x. And what is t? T equals to dy dx. So we are going to have dy over dx equals to minus x e minus x squared over 2 plus c1x. And how will I find y? This y, cross multiply and integrate both sides. So therefore y will now be integral of minus x e minus x squared over 2 plus integral of c1x. We are integrating all of them with respect to s. If I integrate minus x e minus x squared over 2, you observe that what I'm having here is like this. But the difference is just that minus is here. So I'll just copy the answer that I got here. So here that I integrated x e minus x squared, what did I get? I got minus e minus x squared. So therefore, integral of minus x e minus x squared to be plus e minus x squared. So y equals to this is equals to is equals to plus e minus x squared over 2. And if I integrate c1x, c1 is a constant, it will be c1x squared over 2, then plus another arbitrary constant, c2. Because we integrate, we have to add another constant. So that is how we will solve this particular differential equation by using reduction of order. The variable y is absent. Now let's now move to case 2, whereby the variable x now, the dependent variable x is no longer there. Okay, so case 2 now. When the independent when the independent variable x is absent. When the independent variable x is absent. So for example, let's solve the square y dx squared plus the y dx all squared equals to 1. Let's solve this simple differential equation. You observe that x is not there. So now how do I solve this? We start by saying, okay, let's say this is 1. Another example, suppose we are having y, the square y dx squared plus the y dx all squared equals to the y dx. So look at this differential equation. You observe that x is not there, it's only y that is showing. So let's start by solving the first one, number 1. The square y dx squared plus the y dx all squared is equals to 1. The same approach, we say let t equals to dy dx. But then the difference between the first case and the second case is that from here now we are going to use chain rule to make another transformation. If t equals to dy dx, you know that the square y dx squared, the square y dx squared, normally it will be the t dx that we all know before. But then if I want to get the t dx by using chain rule, given that t y is a function of t, so the t dx will be the t, the y, and the y dx, right? This is chain rule now. The t dx, right? The t, the y dx, the y will cancel out. We are going to have the t over dx. So the t dx is equals to the t dy times the y dx. This is chain rule. You know, in the previous case, we just stop at the t dx as the square y dx and substitute back. But then because of this second case now, we take another step. You transform this dt ds into the t dy dx. This is chain rule. And what is dy dx from the beginning? Dy dx is equals to t. Therefore, the t dx is equals to t dt dy, which is our what? Which is our d square y dx squared. So in that case now, substitute for dy dx and the square y dx squared back into our differential equation. So if I substitute for the square y dx squared, the square y will be t dt dy plus dy dx is t equals to 1. You observe that from second order, we break it down to what? First order. How do I solve this? Divide both sides by t. So if I divide both sides by t, we are going to have the t over dy, t over t, that's 1, equals to 1 over t. So this one, we don't need to use what is it called? Linear equation. It's not a linear equation. We can actually use variable separable here. If I bring this one to this side, we are going to have the t dy is equals to 1 over t minus 1. And what is 1 over t minus 1? So 1 over t minus 1, that's the t dy. 1 over t minus 1 will be 1 minus t over t, right? 1 over t minus 1. Yes. So from here, we can use a variable separable, cross multiply. T dt equals to 1 minus t and dy, right? T will go to t side, y will go to y side. If I divide both sides by 1 minus t, so we are going to have t over 1 minus t dt equals to dy. Then we integrate both sides. So if I integrate both sides, we are going to have integral of t over 1 minus t dt equals to integral of dy. How will I integrate 1 t over 1 minus t? You remember integration by partial fraction? Yeah. So when we are having improper fraction, we use polynomial division here, t over 1 minus t. If I want to divide t by 1 minus t, this is 1 minus t, right? 1 minus t. T over minus t, that's minus 1. Minus 1 times t, that's t minus 1 times 1, minus 1. So this will be 1. Minus 1 is the quotient, 1 is the remainder. So this t over 1 minus t will now be integral of the quotient plus the remainder over 1 minus t, right? Or we know how to break a polynomial into quotient and remainder. So if I integrate dy, that as y, let's say plus c1. So integral of minus 1 with respect to t, that is minus t. Integral of 1 over 1 minus t, that will be ln 1 minus t. But then we need to be very careful because of the minus that is here. So this one will be minus ln 1 minus t equals to y plus c1. But then we need to do what? We need to go back to where we are coming from. We must make t to stand alone. How will I make t to stand alone? We are having minus t minus ln 1 minus t. Then I need to make t to be the subject of the formula. What can I do? So if I assume that let's check again the square y. So I made a mistake. This is dy dx all squared. This will be t squared. Sorry, dy dx all squared. That's t squared. So if I divide, sorry, there is a mistake. If I divide by t, so this one will remain t. This one will now be 1 over t. And then I will transform this. This is 1 over t minus t. Then we are going to have something different. So what is 1 over t minus t? So 1 over t minus t will be 1 over t minus t will be 1 minus t square in that case, right? So 1 minus t square over t, then cross multiply. This will be 1 minus t square, 1 minus t square, integral of 1 minus t square. So in that case, we don't need to use integration by partial fraction, because we can actually say let u equals to this, then du will cancel this. So if I say let u equals to 1 minus t square, we know how it's going to be now. So this will give us minus 1 over 2 natural log of 1 minus t squared, right? Yes. So equals to integral of dy as y. Let's add c1 minus with ln. Based on what we said from the beginning, we can bring this to this side. So this one will now be ln 1 over square root of 1 minus t squared. I hope you understand how we got that. Because if this minus go to this side, it will be something like this. And because of minus, it will turn to fraction. So we are going to have this is equals to y plus c1. But then we need to make t the subject of the formula. So what can we do to make t to stand alone? Suppose that c1 is a constant. Suppose I introduce logarithm here. Let's say we are having log c1 for example. So if I'm having this and log c1, because if c1 is a constant, minus c1 is a constant, e raised to power c1 is a constant. Anything we operate with this c1 will still give us a constant. So if C1, if I introduce log C1, yeah, so that log will make this thing easier for me. So let's say ln ln. So collect like term. So if I collect like term, we are going to have does it need, okay, ln well, we can actually do it without using the logarithm. Take the antilog of both sides. Yeah, if I take the antilog of both sides, we are going to have 1 over square root of 1 minus t squared equals to e raised power y plus c 1, right? If I take e of both sides, and you know from indices that e raised power y plus c1 is like e raised power y e raised power c1. We already established that c1 is a constant. Anything we operate with c1 will still give us a constant. So we can say that e raised power c1 is a constant. Let's say a, right? So from here now, we are going to have 1 over square root of 1 minus t squared equals to a e raised power y. So why are we going why are we going like this? Is because look at where the position of t is. We need to make it the subject of the formula. So we need to do a lot of manipulation. So the next thing I'm going to do here is that I will take the square of both sides. If I take the square of both sides, we are going to have 1 over just 1 minus t squared. If I square this a, I will have a squared. If I square this e raised power y, it will be e raised power 2y. Then cross multiply. So 1 minus t squared multiplying by a squared e raised power 2y equals to 1. Divide both sides by this. So if I divide both sides by a square e 2y, so it will now be 1 minus t squared equals to 1 over a squared e 2y. Collect like term. So that will be 1 minus 1 over a squared e 2y equals to t squared, right? So from here now, take the square root of both sides. So t equals to square root of 1 minus 1 over a squared e 2y, and t equals to square root of 1 minus because a is a constant, 1 over a is also a constant. So 1 over a square is a constant. Let's assume that this 1 over a square now, let's say, is equals to k square or anything. And e2y, if I bring this one up, it will be e minus 2y, right? So and what is t? T equals to what? T equals to dy dx. So we are going to have dy over dx is equals to square root of 1 minus k square e minus 2y. And then how do we find y? We cannot integrate directly like this. Unlike the previous example, that what we are having here is a function of y, not a function of x. So we have to use variable separable. Cross multiply. If I cross multiply, we are going to have dy divided by square root of 1 minus k squared e minus 2y equals to dx. So we'll separate now. The next thing is to do what? Is to integrate both sides. So if I integrate both sides, this will be integral of dy over square root of 1 minus k square e minus 2y equals to integral of dx, right? So how do I integrate k square and e minus 2y with square root? If you remember from elementary calculus that anytime we are integrating a function divided by 1 minus x squared, something like this, so our answer will be arc sine inverse of x. So what we are just going to do here is that just write this k square e minus 2y in square form. So we can express it as dy over square root of 1 minus k e minus y all squared, right? So if I'm having, this is e minus 2y, so we can say this is 1 minus k e minus y, all of them square. You know, if you square this, it will be k square e minus y all square, that's e minus 2y, equals to integral of dx. And anytime I'm having, okay, if this is not 1, let's say this is a squared, integral of dx over a squared minus a squared, it will be 1 over a arc sine of x over a, right? So integral of, oh, this is 1 over k e minus y all square, it will be what? 1 over k e minus y arc sine of k e minus y. Yes. So we use sign. Let if it is 1, If it is 1, it will be just sine inverse of x. So, but because if it is a now, if it is a squared, it will be 1 over a. So this is 1. And because of this, so we are still going to have ke minus y. So, yes, if you say let ke minus y equals to sine theta, yeah, it will now be ke minus y dy equals to cos theta d theta. So we are still going to have ke minus y. Yeah, we are still going to have ke minus y. So if I integrate ds, that's x, then let's say plus c2, and final, that's our final answer to this easy looking differential equation, but it's somehow difficult to evaluate. So that is how we solve that. So viewers, I will leave this one for us to practice. So we'll just make dy dx, let dy dx equals to t, then it will take a step further than the previous case from here now. So I'll just give us hints of how to solve that second one. So you can just pause the video and watch it back again to evaluate it properly. So I will not solve this one. I will not solve it totally. So I'll just give us the hint of how to go about it. So the prerequisite of this topic is calculus and all that we've done in first order differential equation, because that's the main tool we are using here now. So we are done with example 1. That example 2 now. This is the example 2. So we are told to solve y d square y, sorry, so we are told to solve y d square y over dx squared plus dy dx all squared equals to dy dx again. So you observe that the independent variable x is no longer there. So we start by saying let dy dx, I'm tired of using t, you can use any letter, let's call it r. You have to be familiar with different variables. Let dy dx equals to r. Then if I differentiate further, the square y dx squared, normally it will be dr dx now. But then if I want to change the r dx using chain rule, so dr dx, if y is a function of r, so dr dx will be what? It will be dr dy, right? I want to get dr dx. That means I'll put dy here and I'll put the x here, so that these two guys will take care of each other. So dr dx is equals to dr dy dx. And what is dy dx? Dy dx is r. So that means this dr dx is equals to this one is r dr dy. And what is this? The square y dx squared. That is the solution we are going to use. But for case 1, if dy dx is r, the square y dx squared is dr dx, then we continue solving. So substitute for dy and the square y into this differential equation. This will be y, the square y dx squared is r dr dy plus dy dx all square. So dy dx is r squared equals to dy dx again equals to r. So what are we going to do here now? I will first divide, let's divide by ry. If I divide everybody by ry now, so we are going to have the r dy, r squared divided by ry over ry. It will now remain 1 over y with r, right? If I divide this one by ry, it will now be 1 over y, right? Because r will take care of each other. So what type of differential equation is this one? It's a first order, but then it falls in which case? This one is not a linear differential equation, because yes, it's a linear. It's a linear differential equation. Dr dy plus r with a function of y equals to another function of y. Suppose we are having r here again now, or let's say we're having r squared. So r squared now is now a non-linear differential equation that we normally use Bernoulli method or whatever. So you continue solving by taking the integrating factor. Integrating factor is exponential integral of 1 over y dy. Integral of 1 over y is ln. This is exponential ln y. E cancel ln. Our integrating factor is y. So if y is our integrating factor, you can continue from there to solve this. So I will leave the remaining solution of this one for us to do, because this is a linear. We'll solve it like 3 times in this video. So basically that is how we solve